So in the TSS, you're including the essentially inert solids, and that probably is where the challenge. I'm just thinking of what we did in the James. It was really difficult to do because you got to do sediment transport almost to some degree. So I sort of walked away from that and tried to come up with means, get the central tendency. So how well in the inert solids, you're not really doing sediment transport like you are for the sand silt clays, is that correct? You're just sort of like...
Oh, no, we use the sand silt clay.
Oh, you use the sand silt clay, okay.
Yeah.
Oh, all right.
Yeah, we use the sand silt and clay.
Okay.
Okay, so let's see, what's next? Okay, yeah, look at second bullet. Concentration of inorganic solids is obtained as a sum of fine clay, clay, silt, and sand state variables. So they come from a sediment transport model. The organic solids, what we do is, all right, when you measure total suspended solids, what you do is you filter the water, basically, you dry it, and you weigh what's there. Okay. And then so that's total suspended solids. Then you put that in a little oven and you burn it, and what goes away is called volatile suspended solids, and what's left is dirt. So the volatile suspended solids is an indicator of organic matter. Basically, you say that what was volatile is organic. Not entirely true, but good enough. But in the model, we do not have volatile solids as not a model state variable. What is a model state variable is particulate organic carbon. And you would also say to yourself, particulate organic carbon must be related to volatile solids, you know, if they're both organic. If you just think of organic matter being CH2O, then the volatile solids ought to be 2.5 times the organic carbon. We actually did a regression, and you see that the organic solids, the volatile solids, is 2.9 times the particulate organic carbon. So if you look at the model code, what we do is we add up all those particulate carbon state variables, we multiply by 2.9, we combine that with the sand silt clay, and we get total suspended solids for use in our attenuation equation. Minor hitch, recall that we had a negative function with salinity. So on occasion, if you got really, really high salinity in the lower bay due to some event, you would compute negative, and coincident with low suspended solids, you would compute negative attenuation. If you want your model to crash fast, do that. So we impose a minimum KE of 0.15 per meter, just to prevent negative values. So there you have that.
There would be attenuation anyhow in blue water, so that's your sort of background.
Yeah.
Okay.
What else have we got here? Practical details. Okay, couple of things. Our regression picked up actually almost no impact of chlorophyll on attenuation. Now we know chlorophyll attenuates light. Like I said, that's how the algae get their energy. But I think what happens is because chlorophyll is correlated with total suspended solids, chlorophyll goes with algal carbon. Algal carbon is a function of solids. So once you relate attenuation to solids, trying to get an additional contribution from chlorophyll, regression won't pick it out. This has attracted some criticism from people who said, yeah, but you know, if you implement a TMDL and you reduce the chlorophyll a lot, surely the attenuation is going to go down. So some of our reviewers have said even if the marginal contribution, well, some of our reviewers have said you got to get that chlorophyll in there. We haven't done it yet. But anyway, I'll just mention that's the state.
But aren't you, in a sense, you're accounting for it in the TSS?
Yeah.
Three carbon groups in there.
As I said, people just wanted us to have a specific chlorophyll And I got to level with you, we could do it, but you know, at the time they said it, we were just burdened with so much stuff. Okay, but in the model code, if you wish to specify attenuation from chlorophyll, it's there. You can do it.
But then again, since you're already accounting for it in the TSS, the normal coefficient, if I can use that number, is like a 0.017. You have to make that a lot lower.
Yeah.
Okay.
I mean, what we could do, well, all right, here comes the deep weeds, but okay. Actually, the attenuation by chlorophyll is pretty well known. It's almost a physical constant. And what we could have done was to go back to the original measures, correct those for the chlorophyll attenuation based on observed chlorophyll and that physical constant, and then do a regression on the corrected values. And you know, it's straightforward. I could have done it, and like I said, we had a lot of other things going on, so we didn't. So for the moment, we're going to let that be. But I'll just mention, you know, repeat myself, if you care to do it, have an attenuation based on chlorophyll, the code allows you to do that. The code will also allow you to differentiate the attenuation from fixed and volatile solids. Again, it's coded in there. We couldn't detect it in the database, but if you happen to want to do it, the code lets you do it. The code allows for the spatial variation of the background attenuation. We do this. You know, I showed you that we found some fairly consistent deviations from that long-term average. So we use a little higher value in the Mattaponi and a little lower value in the lower Potomac, that sort of thing. So we do that. The code allows you for spatial variation of attenuation from solids. We don't do that. If you choose, we're going to look at the file in a moment. Email from Lewis. If you choose to implement the spatially varying option, then you will need to specify 11,000 values, because you need to specify one for each surface cell, and there's like 11,000 surface cells. So in the bay, well, that's not even a big file in certain terms, but in any event, if you choose to make a spatially variable, you need 11,000 surface cells. Go ahead, Jim,
and then
please.
Any of the layers below the surface are assumed to use the same value as the surface.
Yeah. Practical details. Is there anything else in this chapter we want to speak about?
What is the physics behind the spatial variation of background?
Well, as I mentioned, for example, we seem to see a higher background in the York and Mattaponi, and you could see that we saw it elsewhere as well. That tended to be associated with segments which are adjacent to wetlands. So our feeling was that the wetlands are contributing something, color or something to the water. There were places where it was lower. I can't really tell you. My suspicion is that, you know, remember, we don't really have any good measurements of color. We can relate it to salinity on the average, but I think there are going to be places in the bay that for one reason or another have more or less color, and we just don't have the observations and can't deal with it.
Oh,
But
so
that's
the background already considered some of the, like the colors.
Yeah.
Okay. It's not just pure water.
right. Yeah, it's just what is observed that can't be accounted for by solids or salt. That's how to put it. Let's see. Oh, look at that partial attenuation model. I don't know if I want to go into this or not because I'm not really prepared, but in the report you have a tabulation of these adjustments that we made to the background. I'm actually going somewhere, and like I said, I'm not prepared for this, but what the heck. Yeah, this is something we call the absolute mean difference. think of this as being the error or the difference between the observed and computed light attenuation. And we've got the advanced optical model in blue and the partial attenuation model in red. And then these are various subsystems. And actually you see that the error in most cases for the partial attenuation model is lower than for that advanced optical model. And you know, I'm not criticizing advanced optical models, I'm just saying that practically this simple relationship is a good one to go with. I think there was one system where, yeah, the Potomac, the advanced optical model did better. And actually that was one of the systems where I won't mention names, the fellow who did this had a really fabulous data set of optical properties. What had to happen was, you know, with the optical model, you know, we have 11,000 surface cells. You needed to specify optical properties, color and scattering and whatnot for all 11,000 cells. And we didn't have those observations, so we kind of looked at, we in general, well, this embayment kind of looks like that place where we did have measurements, so we'll transfer those values. And, you know, there you have it. So I didn't know I had that graph available. Anything else worth seeing? Okay, well, I'm done with the lectures for today. It's 11:30. I don't know, that's probably early for lunch. Do we want to, anybody, you want to take a break for half an hour, or what do we want to do? Any ideas?
I have a question.
Oh, okay, that's good.
So for the salinity effects, like is a historical preference to add into the growth rate instead of adding a mortality rate for accounting the salinity toxicity effect.
Could I hear that again, please?
So when you account the salinity effect for the algal growth, you put the function into the growth rate instead of the.
I think we actually, it's a mortality rate, a mortality term.
Okay.
I think you could do it either way, but what we do is, if those freshwater algae go downstream, we kill them. And if those saltwater algae go upstream, we kill them, you know. Okay. All right, if I got 30 seconds before we break, and I hope I don't regret this, let me,
could you know, I'm not trying to make it difficult, but could you had at one point a really good relationship, you know, you used to do the game of doing the total PO4 as being the dissolved plus the algal, you know, varying that as a function. Mm-hmm. Was it computational burden that caused you to drop that, or?
You know what all right, Jim is very first model that we did, going back to about 1990 or so, our algal stoichiometry, the phosphorus to carbon ratio, whatever you want to call it, in phytoplankton is not a universal constant. You can get some very good average values, but it's not a universal constant. It's not only not a universal constant, but algae, in contrast to things like people, they can actually change their composition. You know what it is, if there's not a lot of phosphorus around, they'll change their composition. So we, in the original model, we actually had this variable algal stoichiometry, and we made, it was sort of like a partition coefficient. So if the phosphorus was abundant, the algal composition was high. If phosphorus was scarce, it was low. And that had some wonderful properties. But you know what happened was that, for example, if algae sank, they'd have a very thin composition on the surface, but because it was like an equilibrium partitioning, when they got to the bottom, they got fatter, or they took up more phosphorus. And that, physiologically, that didn't make sense to me.
Because of the fact that they weren't growing.
Yeah.
Okay.
So, you know, when I kind of detected that, I said, I really don't like this. I guess I could have done something differently, but the fact that as they sank into phosphorus-rich waters, they took up more phosphorus, right, I didn't care for that, so we did away with that.
That's the main reason, I see.
Yeah. I'm trying to find the model source, and we're going to look at reaeration maybe. I don't know if we're going to do that or not. Let's see. I may hate myself for this. I hate myself for leaving my glasses back in the room. That's one thing. All right, let's look at this one.
Which is, you passed it.
Yeah, I don't know. Okay, reaeration. But I need to find where KRDO is computed.
You want to do a /KRDO?
Well, this editor, I think I can do it this. Ah, there's a whole reaeration subroutine. So, just for the heck of it, so you see that there's an if statement. If you specify wind, and the model input, if you specify wind, then we're going to go through this drill.
Now you are doing the velocity over depth.
Okay, so KRDO is square root of V of B. Okay, B is a box. Okay, so what we're using is, what we're doing is we're using the surface velocity because we only compute this in surface cells. So the answer to that question is for that U over H, we're using surface velocity, instantaneous surface velocity. Okay, and you can see we're, I know because I know model state variables, we're dividing by the total depth. Okay, so the answer to the question was surface velocity, total depth. And
so one more quick question, Carl, thinking about that. If you have 4 interfaces, is that velocity the sum of the 4, or, you know, because you only have one velocity there, and maybe that's in the main direction of flow?
Where are my, we got to figure that. Take velocity over depth. Vel of B.
Oh,
Vel of B.
Oh, never mind.
No, I must have computed that. Vel of 0 is 0. Vel is the maximum. Okay.
Oh, so it's the maximum.
It's the maximum of the 4 faces.
Okay.
And I think I did that. All right, it's the maximum of the 4 faces. Good enough, you know. Okay, we're gonna take a break. If you choose to eat at 11:30, good. If you don't, your choice. But if we have more questions, we have time for questions.
So just you know, like in some cases, the wind is mild and the velocity is mild. Do you add them up, or in this case, just one?
Well, in this version of the model, you specify what you want to do as an input. In previous versions, I computed both and took the highest value.
You took the highest. Oh, okay.
And I really don't. No. I don't know of any formal way of combining those impacts. I've never heard of such a thing. So take the biggest one. If you said I'm going to add them up, you know, it's kind of up to you, and see how well it works. Please.
For the predation term, if I remember correctly, I try to compare it with the EFDC ICM. In EFDC, it looks like it's a linear, so it's the first order with respect to the biplan biomass. So I guess like there maybe must between the first order and the second order because of the saturation of the predation. So if there is an abundance of phytoplankton, there is a growth rate for the zooplankton maybe stable, they become constant, then it will just linear related to the platinum biomass. Is that correct? Right? So the predation term will be linear related to the platinum biomass if there is an abundance of phytoplankton there. And is that the case in the Chesapeake Bay?
Well, you know, empirically, just strictly empirically, in Chesapeake Bay, when we tried to simulate biomass and primary production, our model worked a lot better for what I call quadratic predation. Between you and me, that was the first thing. It works better. Why? Or can we rationalize this formulation? That's when you bring in the thing of the zooplankton biomass is proportional to the algal biomass. So it's really, mostly it's a function of what worked better, and the quadratic worked better. The reason EFDC has linear or first order is because this model used to be first order, and what's in EFDC is, yeah.
Is there any temperature adjustment term for reaeration?
It's looking like in this particular formula I don't think, well, wait a minute now. Yeah, this for wind reaeration, you see temperature comes in here. Now, I didn't go into exactly what this formula looks like, but you see that temperature does come into the equation. It looks like for the function of the O'Connor, the velocity over depth, it looks like I've neglected a temperature correction.
Yeah, on top of that, I think here KRDO kind of calculate coefficients only. But when you really get the quantity of reaeration, it's basically also based on the difference between solubility, right?
Saturation.
Saturation.
Yeah.
In that saturation, calculated based on temperature.
Yeah.
So basically you can.
Yeah.
Yeah, the saturation definitely takes temperature into effect. Yeah, I know. You know, there should be.
No, I was thinking like I don't know, like if same velocity or same wind, whether temperature 30 degrees Celsius or temperature 5 Celsius will make any difference.
The one here, the wind one has it. The O'Connor one does not. Formally, it should. And I think I probably said, you know, this is only an approximation anyway, so I'm not going to bother. We could put that in there.
I think most times the correction value that is used anyhow is like 1.024, so that's a pretty small, as opposed to 1.08 that we normally use for other things. At 10 degree temperature change, 102.4 might be 50%, and that's probably, as you said, sort of within the noise.
So in EFDC plot, which is based on the original ICM, there's a temperature adjustment.
Mm-hmm.
That's why I'm asking if the new one still have that.
Mm-hmm. Yeah, clearly looking at the code, we've neglected it. Okay, is it lunchtime? Or break time, or whatever we want to do? Okay, so we'll get back, let's get back at 1 o'clock, and what we're going to do at 1 o'clock, we'll pick up with some actual model exercises. Okay, fair enough, thank you.